We'll continue with the morning session, and we have Alexandros Askounis from Wolverhampton talking about evaporation of inclined drops from experiments to theory.
Thank you. Thank you for the invitation as well. I'm from there, yeah. So the thing I'll be talking about today is evaporation on inclined droplets. I think you had a very nice introduction from Anna. Anna is sitting there, by the way. She told me to not put her on the spotlight, so I'm doing my best on that. So we did some experimental observations when I was here at UEA a while back now. And since then, we've been working on trying to explain what's going on in there. So first of all, a little bit of context. Why droplets? They're everywhere, technologically speaking, but also in nature. Then we have biomedical diagnosis, air conditions, heat and thermal and cooling. So there is pretty much everywhere. I'm going to skip this slide because I understand that there was a session on evaporation anyway. All you need to take away from this, because it might be useful later, at the contact line of the droplet, evaporation is much faster than at the center, which is something Alex and his team at Strathclyde have been very involved with proving and showing the mechanism behind. That creates and induces a flow that brings the interior, the bulk fluid to the exterior, to the periphery. Together with bulk, we also have particles or solids that are inside the droplet moving there, and when they evaporate, they create a coffee stain. This coffee stain is typically not liked, but in some cases, when you want to make a crystalline structure, for example, we can tweak that and get something very nice out of it, and so that may become advantageous, let's say. Now, once upon a time, I was back in Greece visiting. There was a rainstorm. Something like this happened on the car. And I was thinking, why do the droplets look so strange when in everything that I've been working on for the past 15 years, they look quite symmetric? And that started making me think, why are we only looking at symmetric droplets? Obviously, it's easier to understand, easier to explain. But then I was intrigued. Let's change them. And this is just the windshield, right? You see this on your windshield when you drive. You see the raindrops are never very symmetric, very perfectly looking. And the second thing is, when I was doing my PhD, I bumped up across this paper from Matar's group where it's talking about some sort of terracing that the particles have at the periphery of the droplet. If you're wondering what is this, it is at the very edge here, okay? So at the very front end. And this is just an analytical approach. This is the experimental result that I got back in the day. This is from an atomic force microscope. And if you're wondering where are the terraces, they're there. So this was the slide I had about experiments, and then I was supposed to talk about what we've been working with Anna, but then she told me she beefed up this talk about being hyped up this talk about being experimental. So now I have to show you some experimental data. Did I put you on the spotlight again? Sorry. So the problem we have with inclined droplets, we don't know what's going on. If you see on the left, people claim that as you increase the inclination angle, the evaporation time or lifetime or whatever you call it, the phenomenon lasts longer. You go from black to blue. But on the other side, you can see the opposite effect. And then we're wondering, what's really going on? My assumption always was that there is local saturation here, which drops this evaporation rate, and there is an increase in the evaporation rate over there because the angle drops rapidly. And this is what Strathclyde group have shown in quite a few papers. But is this the case? And then what about the evaporation flux distribution across the interface of solid and liquid? So these kind of questions started making me think what's going on behind the scenes in the experiments. I did some literature survey, found some very nice images showing the flows in there, and you can see there is some sort of an effect of gravity. This is the no inclination, and then when you have the extreme inclinations, you see that a sort of a vortex starts to appear. Then we're wondering, why is that? Elsewhere, the solids also change their deposition pattern. So there is a lot of indications that the flow is affected. The internal flow within the droplet is affected. How? Because of the evaporation rate at the two edges being not similar. So this is what I'm trying to explain in this talk. I hope I will do a good job. You will tell me at the end. Experimental observations. Again, thank you, Anna. We did these few tests. Here are the actual conditions. What I want you to look at here is this is the no inclination case, and then we increase inclination to 20 and 40 degrees, and we are counting this as the angle of inclination. Okay? And now we are thinking that the gravitational effect has two components, one parallel to the surface and the other not so much. So that is kind of our analysis. Now in my talk from now, you will be looking at this as the top side and this as the bottom side to help you follow it. Okay? Now, the one thing you will notice first and foremost is that actually the evaporation changes rapidly with inclination, yeah? And you see that we go from something very symmetric to something that has a longer and longer tail. And actually, this is not fully depinned and moved away. The droplet has a liquid, it has a continuous small film. And I say small, not thin, because we haven't managed to quantify it yet. So this is still a film which is not fully disappearing until the very end of the evaporation. Okay. The other thing you need to notice here is that the droplet is pinned at both ends across the evaporation cycle. So enough with this. This also comes with videos, but I only have 30 minutes and the videos take 30 minutes each. So I'm going to skip them. Here is the gist of it. Basically, we have the base diameter, which is this distance here, self-explanatory. The contact angle, this contact angle without the subscript is the average left and right. Then we have the front and the rear, the top and the bottom respectively. And you see how they are affected by inclination. You see the blue and the green, how far apart they are. And now I started looking at this data and thinking, and I forgot to say that the volume is coming out of the software that does the analysis of the rest of the values. It's just a fitting of the image. It's image processing. ImageJ can do the same if you're interested. So basically what we've got here is a nice indication of, I don't know where we are based on the two other cases that I've shown you. Is the inclination increasing or decreasing the evaporation? It's not as straightforward as we initially thought. So we did a little bit more look into it and try to analyze and create some sort of evaporation flux. And here is where we take the Huhn-Larsson. For those who don't know, Huhn-Larsson wrote a seminal paper following Deegan's paper on how droplets evaporate. And this is pretty much their equation. This is a diffusion limited equation. And it is predicting the evaporation flux for a case that is the droplet is flat. Now, we are normalizing with that, whatever we're calculating when we have an inclination, okay? And we end up with something that looks like this. And I think this is the heaviest mathematical slide I have. You will help me after. So basically from this one, we then take this actual size or value, and we plot these arrows. These arrows are showing the evaporative flux that is tangent to the liquid surface interface, to the liquid surface, no, to the liquid air interface. And the actual length of the arrow comes from this value. So they are kind of showing the differences. And indeed, you see how bigger this is compared to that one. Yeah? And we believe that this one is the reason for all these changes in the deposition mechanism of the particles and the evaporation phenomena and so forth, because each one of them arrows, if you do a height average analysis, you will see it induces an outwards flow from the center of the droplet to the edge or the other edge. How strong is that? Flow is dependent on the actual size of the arrow. It's easy to see it now. It wasn't as clear when we were working on this. And when I talk about deposition patterns, this is what I mean. And you can see how nice and symmetric this baby is, you see? But then look how awful this looks like. And this is exactly the effect of inclination on the evaporation rate that induces these deposition patterns. Now, I also put a blow-up of the top and bottom cases because I wanted to show you this one. This one is with a laser scanning microscope, a very nice facility we have here at UEA. I said we, apologize. So over here, you cannot see any terraces yet, but we will get to the terraces in a moment. What you can see is roughly the change of the shape based on the, let me say this again, you can see the change of the shape of the deposit of the ring based on the inclination at the top and the bottom respectively. And what do we get from that? We get that actually, if we consider that the liquid front is kind closely related to the available space for the deposit to happen, we actually get to see whether or not this validity works. Okay, so this is an indirect validation, not a very proper one, but it is crude like many observations are. So further to this, we now have a blow up exactly at the leading front, and you can see, I was hoping you could see it a bit better, there is a nice terrace over here of particles, and then the next terrace appears, and they appear very nicely periodically whenever we have a 1 microsphere particle. Okay, now please note how many steps we've got on the top side. The top side is the thinner side. Okay, keep that in mind for a second, and look how much it changes when we go to the bottom side. Why am I pointing this out? Because this is the available space. There is always a balance between how much space is available for the particles to go and deposit with how many are there and the actual disjoining pressure, structural disjoining pressure at the wedge front or back, top or bottom, sorry. So basically, for me, this one is the clearest, but the last one as well. Okay, and also we have changes in the width and all that. And now this is what we have been trying for the past, how many years, I don't remember, with Anna and Mark to work out an explanation for, to which I will be moving on. Prior to this, before I left UEA, I had a very good student who was very good with COMSOL, Ahlem. She did some crude analysis with COMSOL to begin with. Here we validate that the model works for a flat droplet, and then the results is giving us a very nice, where is it? Quantification of the actual arrows based on COMSOL. COMSOL is fantastic and good in this, it can solve it, but it's not always clear what it is actually solving behind the beautiful interface, yeah? So this is what the droplet would look like at equilibrium, and this is what the contours will look like, the flows will look like inside. And we see that as we go from a almost symmetrical left and right flow pattern, everything collapses to something that has a very big vortex here and a tiny one there. And that, for me, is a very good enough proof that actually the evaporation-induced, what did I say? Yes, the evaporation-induced internal flows are heavily impacted by gravity and inclination. Now, with Anna, we built another model based on Matar's paper from 2009. She did that yesterday, so I'm not going to go into the mathematics of it. If you have any questions, she's here to answer. She's there. However, what I want you to, where I want to bring your attention to is the evaporation flux. For me, this is the driving force. This is what is making things happen. And you see at the peak, at every step, we have evaporation flux at the very edge. And that is what is driving the concentration to go up there, together with viscosity and everything else. And we get some formation of terraces with the blue line over there. And this is where we are at this moment, and we're trying now to validate all these things. Now, when I say validate, I mean this slide. And here Anna is plotting from left to right the terraces as they would look like. Of course, there is an assumption that there is nothing in between. There is a lot in between. In our cases, it's not, but imagine the other side as well. And I think qualitatively at this point in time, we have a good agreement. However, this needs further refinement to actually see how many different terraces appear and why. Okay, because there are too many parameters at play. We need to identify which one is the main perpetrator. Yeah, English is not my forte, you can see. So basically, what I'm showing is that we can do experiments, but we do need the help of some good modeling to understand what's going on. So to sum up, we did identify, oops, they should be coming up the other way around. Okay. Technology. So gravity does have an effect on how droplets evaporate. I think I showed that. The main effect is in evaporation kinetics. That evaporation flux at the leading front and the back front, anyway, is the main perpetrator for this. And all these affect on the deposition patterns and the terraces that we saw. And I think I went a bit too fast, didn't I? Oh, damn it. Maybe I have a slide to show you with the droplet evaporating, but I'm going to skip it. I will thank these people here for their contribution, and I will now be taking questions because I was too fast.
Thank you. Any questions?
Oh, not him.
Thanks. That was a really nice talk. The droplet lifetimes that you were looking at, where you sort of weren't sure which direction they were going in early on, on the deposition picture, it looked like the shape of the droplet footprint changed slightly as you changed the inclination. Have you in any way normalized for that in your lifetimes, or is that part of what's causing it?
No, I didn't normalize for it. I just took it as an observation, but it's also part of what I was expecting. So when you place the droplet and you start tilting, you expect that the gravity to take hold. The interesting bit is, following up on this, is that regardless of the size of the droplet, even those droplets that are below the capillary length, even those small enough droplets did show an effect on that. I only stick with 9 microliter droplets because they show the biggest one, the easier one to follow.
Okay, it's just the Hewen-Larson type model is sort of only valid for circular droplets, so the non-circularity is...
You're absolutely right on that. It is an assumption we make, saying that this is the available tool from the literature. We're trying to modify it ever so slightly, and I think we actually did some very slight modification. You will see these terms here. We did modify them ever so slightly to account for that, because I think the model is valid up to P over 2.
Okay. Great, cool, thank you.
Any?
So if I well understood, your drops are static because the hysteresis of the contact angle makes them static. What would change if they would move? I would expect that they would move, then evaporation and stop. But have you considered that, or have you seen?
We definitely consider that, only because as we are doing the experiments and you start tilting, when you do the lower concentrations, they will fall off, or they will make a very finger-like pattern. So yes, we did consider for that, but because the aim was to get a ring and to see how the ring deposit from the Digan seminal paper is affected and how it changes because of inclination, we had to impose a small scratch, that's why I was asking you earlier, to make it stay, and then the particles deposition at the edges will pin it further, and actually to the front, that was the main concern. They never moved.
Any other questions?
Thank you. Thanks, that was really interesting. Do you think that it's possible to go the other way, in the sense that if you see a deposition pattern, could you reconstruct the angle of inclination? is it unique?
I cannot tell you 100%, but my intuition is this. Let me find the slide one moment. In this paper, what I'm saying is that depending on the angle of the droplet,
Mm-hmm.
you will be getting a different size deposit. This is the wedge at the very edge,
Mm-hmm.
where it's safe to assume that the liquid and the particle size, especially there, are one. So I would say yes, but with some doubt. So we need to work on that.
Okay, but actually looking at that details of the terraces, you think
Yeah.
could be enough?
Yeah.
Okay.
But also remember that in most of the papers you will see there is usually an additional film
Mm-hmm.
of liquid in front of the first particle, because the molecule of water is much smaller than 1 micron, and you can get that. So basically, it is valid to a point.
Thank you.
So, from this experimental work, can we have some explanation on the nature of the disjoining pressure that Anna used yesterday?
Anna? The oscillatory stuff.
Yeah, the oscillatory. And can you quantify the effect of disjoining pressure with your measurements?
I don't think we can go directly to quantify them,
Or yeah.
but I think we can validate their existence by saying how the disjoining pressure changes and creates the terrace.
Okay. And
So I think it's an indirect kind of relation, not
it's a
a
reverse.
very clear
yes.
one.
And a small comment. Do you believe that there is a correlation between the distribution of the disjoining pressure with the profiles of the J distribution that you?
Possibly, but I have a bigger feeling that it's not the evaporation profile, it's the actual flow, how do you call it? The arrival, how fast the particles arrive to the edge, that is affecting the disjoining part.
Okay, thank you. Any other questions? Then we should thank Alex again.
Oh, thank you.